And from there you can build a compiler, and this can be used to compile a code. Another option is you can do like cross-compiling for specific target environments, or you can use an existing compiler to build the next compiler. That is the approach that Go uses. That's called bootstrapping. So how does this happen? Like initially, the Go compiler was written in C. So this is from Go 1.0 to 1.5. And then for Go 1.5, that's around 2015, I think. And the compiler was rewritten to Go. And ever since, the Go compiler is self-hosting, meaning that for the next iteration of the Go compiler, if you get the next version, it's built from the previous version of the Go compiler. This works on the basis of like n+1. So if you have 1.26, you can build it from 1.25. So, like, what's the point of all this? Why not just keep it in C? Or like, what's the point of having your own compiler in the same language you're using? So one of the things is like Go has a rich feature set of tools. Some you've used before, like you have GoDoc, you have FMT. So you can use all this to validate and go through the compiler code because it's already written in Go. Another thing is like the advantages that Go provides, like you have type safety, memory safety, and this can only make the compiler better because it's already built into Go. And then another thing is you already have a community of people who know how to write Go. So you already know how to write Go. You don't need to write another language again. So this creates like a self-sustaining community to develop the compiler. And then another thing is like dog fooding. So what this means is you use your own tools. So the Go team uses Go and builds the compiler. So the more you do this, like using your own tools, you will make them better. You will be able to see bugs and like possible areas of optimization, and you can make improvements because you use your own tools every day. Yeah. So how does the process take? Place? So you'll start from Bootstrap compiler. So any version of after Go 1.20 will work. And then this will build the new compiler. You can call it V1. And this compiler will build from the same code will build another new compiler. This is just another version of the new compiler. And these two will be validated. If they match, then we can get the core functionalities on all the modules, standard libraries, everything that Go comes with. And why do we do it twice is for reproducibility and self-sufficiency. So like if we verify that we compile it twice and we get the same result, then we're on a good track. If you go to the GitHub repository for Go, so there are like the key components. You can go through the paths. So you have compile. This is where the compiler is. So you have things like parsing, type checking, optimizations. Then you have the linker. You create executables from this. Like if you have like underlined precompiled things, you can link them. And then you have the assembler. This is low level, now almost machine code. And then you have the runtime. See, this has like the most important bits of Go. So you have the scheduler, garbage collector, memory. Yeah. So we'll do a bit of a demo. This takes a bit of time, so I'm just running it beforehand, but you can follow along on your own computer if you'd like. So we'll go through how the compiler process works. Yes, you can clone and then check into this directory and then just run like bash. This takes like about 5 minutes. So I'll just show the results just a moment. So yeah, let's see the version. Yeah, so this is the new built one. Yeah, that's basically the process of bootstrapping. We'll go back to the presentation. Yeah. Question. Ever since the compiler was rewritten in Go, it's been getting faster and faster. You might have had like one of the advantages of Go is like the fast compilation times. This is just enabled because of like the features we have in Go already. Yeah. So with self-hosting, like you get better optimizations, and it's been faster and faster every year with every iteration. Another thing is contributing is approachable. There's a big community of Golang developers, and if you know Go, you can contribute. It's all open source. Yeah. Another thing is it helps you to understand like performance patterns. With the tools being open, you can be able to see like from the compiler, as we'll see in later slides. You can see which patterns produce like faster code and what are better optimizations, like what you should do with your code to make it faster. There are things like escape analysis, like in Go you have the heap and the stack, and where you allocate your variables depending on how they're used. So you can do optimizations based on that, inline decisions, things like that. We can also, another reason this can be useful to you is, for example, if you want to do a custom build of the compiler, say maybe you have like compliance requirements, or like you want to add something non-standard to Go. Let's say you want to add like a new type of loop. You want to add like I don't know, a do while. The reason you will want it, I don't know, but it's possible. Yeah. Yeah. Next, we'll look at a bit of like how the compiler thinks. So we'll look at an example code, and with the compiler being open, you can give flags to the compiler. So in this case, these flags tell us the decisions that the compiler goes through for optimization when it's compiling any code. Yeah, so let's run that. Okay. So first things first, let me show you the code. Okay, this is, I hope you can be able to see. This is nothing too special. We have like some addition functions, some calculations. You can see like the comments, there's lines of code. This code is like 4 lines in the function. This is another smaller function. Yeah, I won't go through all of the like escape analysis. In this case, we don't have too much time, but the functions specifically designed here that you can see like how things are designed to go to the stack or on the heap. And then some example like with date code, you have like unreachable code, then long complicated function, and then you have main. Yeah. So let's run this way. Let's, okay. Can do this with pretty much any code. It will work the same. Then yeah, should run now. Shouldn't take too long. Let me see if I have like the history. Okay, yeah, I had run it before. Yeah, so for this code, you can see what the compiler goes through as it looks through your code. You can see like some variables are stored on the heap, some are not. The decision depends on like if variable stays like within the scope of one Go routine or if it's global or past another Go routine. Yeah, but that's another talk entirely. Yeah, but you can see basically what the compiler does as it assigns memory. And yeah, inlining like what functions get broken, squeezed out to one line and which ones are not. Yeah, so all that you can go through specifically to see how the compiler goes through all the code. Let's go back. Okay, yeah. So this is basically like what you'd see in this code. In this output, you'll see like the inline decisions, escape analysis. Yeah, and from this you can see like how you could possibly optimize your code. Another thing is the single static assignment. This is from the rewrite of the Go compiler from C to Go. And single static assignment is a concept where like for every like assignment you get a new variable. It will make sense like when I show it a bit more. But in this case, you will be able to see like how the compiler takes in your raw Go code, how it's converted into like abstracts. Into the abstract representation in the Go language, and then finally all the way to like what is the resulting assembly like at the end. So a lot of things will happen there, like you'll get rid of deep code, common sub expressions. You'll see like register allocation, like it will be assembly code. Yeah. So let's run through. Yeah, I think they skipped this one. Yeah. So you can pick any function really from your code, and then you can be able to see how it's taken through the compiler. So in this case, let's start with like a simple one. Let's start with the add function. So yeah. So Go SSA func, we set it to add, and this will create a new HTML file, which will have the static single assignment for that function. I already ran it, so we'll just go over it a bit. Just a moment. So this is the resulting output for it. We'll start it from the end. So this is the add function. You have two integers and simply returned. So the abstract representation, we'll see that next here. Let me center it. Yeah. So basically, you have still variable A and B on stack, both of them, because they don't leave the go routine. And yeah, so you can see like the start of it, you have the static assignment. The variables won't maintain the same name, but you have basically B7 is assigned to integer A, B8 to integer B, and then we call some add function for B7 and B8, and we put the result in B11, and then B11 is returned. Yeah. There's a bit more that happens here, but this is basically the end of it, the generated single static assignment at the end of it. Yeah, so you can do this basically for any function. Okay. So, like another feature we can get is cross compilation, which this is enabled like from SSA. Go knows how to compile itself like in other to compile the compiler for any target, and this can enable you to compile your code as well for any target really, any operating system, any architecture. Yeah. So this is all enabled from like the bootstrapping process. Yeah. So yeah, you can basically try this as a weekend project. All you need to do is like clone the Go source code, and then you can make any small change. You can write your name on the output or something, and then just remake the compiler, and you can use it. You can have your own Go compiler that you can use for, I don't know, anything. Yeah. But another consideration is like with bootstrapping, like you're building the next compiler from a previous compiler. This creates like a trust problem. Like the previous compiler could inject maybe backdoors to the new one. There's a guy named Ken Thompson wrote a paper called The Trust Problem, basically, and how you can prevent this, or how Go does it, is all of this is open source, just restart, and then you have reproducible builds, like you saw the two tool chains that are verifying each other. So you can make sure like there's nothing, there's no money in the middle there. The reproduce compiler is the same, and then yeah. So the reproducibility and openness prevents this trust problem. Yeah. How does the release process for Go on? So you have the development on master. You'll have like your proposals, your pull requests. This one's will get merged, and then we'll bootstrap with the previous version of Go. And then this will go through testing, and then it will be the new release. Yeah. All of this, like what it gives you is like all the tooling available in Go. Like you have things from the build command, you have dry run. You can pass things to the compiler, flags to the compiler to see like decisions, optimization decisions. You have SSA, risk condition detection. Like, there's a lot available from the build command itself, which is based on the compiler. And then, yeah, from self-hosting, like building your own compiler in your own language, like we've seen improvements in compilation times, better optimizations. Garbage collection for Go is pretty good. Another thing is like smaller and smaller binary sizes. And yeah, Go keeps getting better and better.